So in this problem, we're given a feedback block diagram that is shown below, which has a pre-filter, a controller, a plant, and a sensor, along with two different types of disturbances, which are du and dy, as well as some noise n. And in part A, we are asked to express the output y of s as a function of all the inputs. And so now getting started with part A here. Since we want the output y of s in terms of all the inputs, which are essentially all the external arrows pointing into the system, which in this case are r, du, dy, and n, we essentially want to go ahead and express all the signals involved in the system algebraically. And of course here the signals in this block diagram are basically the arrows that you see in between the blocks. So essentially we want to represent these arrows algebraically for this problem. And so how can we go about doing this? Well, for example, let's take our signal y, which is our output, and try to write this algebraically. Now, as you can see, to the left of it, before the disturbance dy, is another signal that comes out of the plant G, which we can call y prime. And so in this case, from control theory, y is essentially represented as a combination of the two signals that come before it, which are y prime and dy. So we can say y is equal to y prime plus dy, just like so. And now similarly, we can go ahead and do the same for the input or signal u, which in this case will be made up of uc and du. So the signal u is equal to uc plus du. And so hopefully now you can pretty much see the pattern for these signal expressions. And now let's go ahead and try the next signal, which in this case is E. And now here E essentially represents the error in the system. And well, from control theory, we know that this error E is equal to the input R minus the output Y. But in this case here, we have a signal coming out of the pre-filter F. And so I'm going to call this signal RF. So now this error is going to be equal to RF minus, in this case, since we have a loop, this will be minus YM. And so that is the expression for error, which represents E. So signal E is simply equal to RF minus YM. And now, what does YM equal to? Well, this is going to be similar to the case with Y and U. So hence, YM will be equal to N plus the signal going out of H, which we can call YH, just like that. So YM equals N plus YH, which is again a combination of the signals that make up YM. So now let's try to write algebraically the signals that are coming out of the blocks instead of going into them. So for example, here let's try writing y prime algebraically. And now compared to the previous signals, what is going to be different here? So let me start off by redrawing this block G that represents the plant of the system. And so we have block G with the signal y prime coming out of it on the right side. And that's going to be the signal out. And then on the left side is going to be the signal U going into the plant. So we'll call that signal in. And so from the theory behind this, the signal out is equal to the block times the signal in. And this, of course, is considering we are in the frequency domain, substituting in the symbols y prime is equal to g times u. And so that is basically the algebraic expression of y prime. And now let's try doing the same for the signal UC, which is coming out of the controller block C. So again, that is going to be the block times the input signal, which is E. So in this case, it's C times E, just like so. And now moving on to the signal RF, which is the signal coming out of the pre-filter block F. So again, block times the input. Here the input to the left of block F is R. So in this case, RF equals F times R. And now the last of these signals that we need is YH, which of course is the signal coming out of the sensor block H. And now the input that's going into H is basically Y, since the Y output gets split up in this junction here. So that means that YH is equal to H times Y. So now we have essentially defined all of the signals algebraically. And now the next step is to pretty much combine these equations by using substitution. So for example, taking a look at the first equation on the top left, we have y equals y prime plus dy. And we have an expression that defines y prime, which is g times u. So we can go ahead and substitute in gu for y prime. So that leaves us with y equals gu plus dy. And now we can try doing the same for the second equation, which is u. Here we know what uc is, so we can go ahead and substitute in ce for uc. So we will get u equals ce plus du. And now we can further expand this equation by substituting in E, since we also have an expression for that, which is RF minus YM. And here we also have an expression for RF, so we can go ahead and substitute in F times R for RF. So this will be C times F times R. And then we also know an expression for YM, which is N plus YH. So it'll be FR minus parentheses N plus YH and plus DU. And so now that we have a more expanded and combined expression for U, we can go ahead and substitute in this new expression of U into our Y equation. So for instance, this is going to be Y equals G times our expression of U. So again, we're substituting in this new expression of U. So this is going to be G times C times FR minus parentheses N plus YH, close parentheses, plus DU, and then plus the dy. So this is our new expression of Y. And now as you can see, we can go ahead and distribute this out. So this will be Y equals G times C times FR, right? Since we're multiplying out this C. So then this is minus C times N, and then minus C times YH. But now actually, before moving on here, you may have noticed that we have an expression for YH, which is H times Y. So I'll just go ahead and substitute in H times Y for YH. So this becomes C times H times Y plus DU, close parentheses, plus DY. And now here we can go ahead and multiply out the G. So this becomes GCFR minus GCN minus GCHY plus GDU plus DY. And now here we can combine the like terms for Y. So this is going to be Y adding the GCHY to the left side, we have y plus, I'll rewrite this term as YGCH, which is again the same as GCHY. And to the right of the equal sign, we are left with GCFR minus GCN plus GDU plus DY, just like so. And now we can rearrange the left side as y times parentheses 1 plus GCH, which is of course the same as y plus YGCH. And then just bringing down the right side. So once we have that, I'm just going to go ahead and put parentheses around our block symbols, just like so. And now we can simply divide the 1 plus GCH from the left side onto the right side. So in this case, we will have y represented by the blocks as well as all the inputs of the system, which are r, n, du, and dy. So after dividing the left term, we will have GCF over 1 plus GCH times r. And now here, I'm just going to go in order of the inputs we see on the system. So that's r, du, and dy. So next I'll write plus g over 1 plus GCH times du. And then for dy, 1 over 1 plus GCH times dy. And lastly, we will have minus GC over 1 plus GCH times n. So now we have expressed y of s, or y, in terms of all the inputs. So this is the answer for A, which again expresses y of s as a function of all the inputs. And next, in part B, we want to express error this time as a function of all the inputs. So again, we know that system error E of s is equal to r minus y. So in this case, we can go ahead and simply substitute our equation of y, which we just found, since this one is already as a function of all the inputs. So I'll go ahead and substitute in this expression. And as you can see here, we can go ahead and combine the r-like terms. So to do this, I will multiply r by 1 plus GCH over 1 plus GCH, which will leave us with 1 plus GCH over 1 plus GCH times r minus GCF over 1 plus GCH times r. And then after distributing the negative, we will have minus g over 1 plus GCH times du minus 1 over 1 plus GCH times dy, then plus gc over 1 plus GCH times n. So now subtracting the r terms, we have 1 plus GCH minus GCF divided by 1 plus GCH times r minus the remaining terms. And so this is error expressed as a function of all the inputs. Now for part C, we want the plant input u of s expressed as a function of all the inputs. And so here we know that we have an expression for u, which is u equals uc plus du, and uc is equal to ce. So in this case, we can write u equals ce plus du, which can then be rewritten as u equals c times rf minus ym, substituting in the expression of e, plus du. And then we can express rf as fr and ym as n plus yh. So this will be c times fr minus parentheses n plus yh, close parentheses plus du. And now we can multiply out c. So we have CFR minus CN minus CYH plus du. And here we have the expression of YH. So I'll just go ahead and rewrite this as HY, which again is equivalent to YH. And then here we also have an expression for Y, which is Y prime plus dy. And then Y prime is GU. So we can go ahead and substitute that in. So hence we have U equals CFR minus CN minus CH times, again, Y prime plus dy, which we can write as GU plus dy, and then plus the du. So simplifying this, we will have CFR minus CN minus CHGU plus or minus CHdy plus du. So now that we have substituted in all of the expressions and expanded out our equation, we can go ahead and combine like terms. So here, for example, we can add CHGU to the left side. So we have U plus CHGU equals CFR minus CN minus CHdy plus du. And on the left side, we can factor out the u. So we have u times 1 plus chg. Or actually, I'm going to rewrite this as gch. And that's equal to the right side. And just like how we did for the y expression, we can divide the 1 plus gch to the right side. Hence, we will have u of s equals cf over 1 plus gch times r minus cn over 1 plus gch minus ch over 1 plus gch times dy, and then plus 1 over 1 plus gch times du. And so that right there is the plant input u of s expressed as a function of all the inputs, which completes part C. Lastly, moving on to part D, we are asked to write the loop transfer function. And so that is basically going to be the transfer function that exclusively represents the loop of the system, which, as you can see here, it includes blocks C, G, and H. And so that is just simply C, G, H.